Welcome. We have done some problems on the liquefaction and refrigeration. We shall be seeking some more problems in this particular lecture. So, in this lecture, we shall be looking into the estimation of the refrigeration effect, the COP, that is the coefficient of performance, figure of merit, then liquid yield, the work requirement for simple Linde-Hampson system and pre-cooled Linde-Hampson system. So, first let us come to this problem. Here we have to determine the refrigeration effect, the coefficient of performance, the figure of merit for a simple Linde-Hampson refrigerator operating between this particular temperature pressure and compressed to this particular pressure. The overall efficiency is taken to be the 75% for the compressor, and the heat exchanger effectiveness is to be taken as this particular 0.96. Then the working fluid in this refrigerator is nitrogen. So, with these information we have to find out the refrigeration effect, the COP and the FOM. So, first what we do, that we write all the data given to us, and in terms of the various notations. The temperature is 300 Kelvin, and that is we are going for isothermal compression. So, this is the compressed from 1 atmosphere to about 100 atmosphere, and this is the overall compressor efficiency, and this is the heat exchanger effectiveness. Now, we for these kind of problems we have to take the help of the TS diagram, and in this case we shall choose the TS diagram of nitrogen, and from that we have learnt earlier how to look at TS diagram, and from there we can find out that what are the enthalpy and entropy at the inlet and outlet of the compressor. So, these are the values we read out from the TS diagram, and then we know that from the because nitrogen is saturated after the isenthalpic expansion at the JT valve. So, we shall be getting the saturated nitrogen and saturated oxygen at 1 atmosphere. So, these are 1 atmosphere. So, there we are reading from the TS diagram the values of the saturated vapor enthalpy and saturated liquid enthalpy. G is for the vapor and F is for the liquid. So, from the expression we have derived earlier for the work per unit mass of the gas compressed. So, here we are writing the expression, and we are plugging in the values of temperature, entropies, enthalpies, and the overall efficiency of the compressor, and we find that this is the work required for this refrigerator. And from now we come to this expression for the how much heat is absorbed, and this is the expression, and in this we have the heat exchanger efficiency, and we again plug in the values of the various variables, and we get this value. This is the refrigeration effect. That means the this particular gas under this particular situations will be taking out this much amount of energy from the space to be cooled. Now, to find the coefficient of performance, we know it is equal to what? Is equal to the amount that is heat absorbed and the work done on the system. So, we are again plugging in the values, and we are finding the coefficient of performance is coming to be this value. And now, to compare that how good or how bad it is, what we do, we compare it with the ideal value of the COP, and that is for the Carnot refrigerator, and here we put these values of this COP ideal, that is Tc by Th minus Tc. We put these values and we find this is the value of the COP, and we can easily compare that the real refrigerator has much less COP than the ideal one, and to assess further we find out the figure of merit, and we find the figure of merit is coming to a very low value. This is about only 4.6%. That means it is it is not a very good refrigerator. It is because it is giving a very small value of the FOM. Now, we come to the second question. In this question, we have been asked to consider a simple Linde-Hampson system using nitrogen as the working fluid and also a pre-cooled Linde-Hampson system using the same nitrogen as the working fluid and Freon 12 as a refrigerant, because in the pre-cooling system, pre-cooled system, we need a separate refrigeration circuit. So there, that is why we are finding in the refrigerant circuit system for this particular pre-cooled Linde-Hampson, we are using their Freon 12, and with this information we have to determine the liquid yield, the work requirement per unit mass of gas compressed, and work requirement for the unit mass of the gas that is liquefied. So these are the ones we have to find out, and we have to also find out the figure of merit. Now here in this particular diagram, what we see, we are showing the TS diagram for the simple Linde-Hampson which we saw earlier. So here we are finding that pressure is increasing at constant temperature, and then at constant pressure there is a cooling, and then at certain point we are making the isenthalpic expansion jetty valve, and we are getting the two phases, and the vapor phase is taken back after heating to the inlet condition of the compressor at a constant pressure. Now, as per the problem, these are the various values given to us. So it is from 1 atmosphere to 200 atmosphere, it is being pressurized at 300 K. So this is the 300 Kelvin line. And for the pre-cool system, what we have been given, that we are asked that we are taking the Freon as the pre-coolant, and for this system we have been given, this is the, understand, this is the actual refrigeration cycle and this is the pre-cooling cycle. So first let us see in the actual one, we have the 300 K same as the earlier, and 200 atmosphere, this 1 atmosphere, and only thing modification is this, there is another thing this coming for the pre-coolant. Okay, this 36 is showing the pre-coolant circuit. Now this is pre-coolant heat exchanger, and here we have been given all the values of this HA, HB, HC, etc. as per our earlier. You can refer for this one, you can refer to the system we have shown in the lecture. So there you can find out what is A, B, C, D, and you can also make out from here that what is A, B, C, D. From A you are isothermally compressing it, so A must be this 0.1, all these things. This similar kind of thing will be there for the this pre-coolant. So you can see that if you can plot this one also in a TS diagram for the pre-coolant. Here we are showing on the pressure enthalpy diagram, but you can make a similar kind of diagram on this TS diagram also for the pre-coolant. So this is please understand this, you can solve these problems by taking in consideration any of the thermodynamic phase diagram. It is not that you have to use TS diagram only, you can use any thermodynamic diagram. Only thing is this, if you choose one particular diagram, you may find that the solution becomes easier to do. Otherwise, there is no restriction that you have to use the TS diagram or pH diagram only to solve this kind of problems. And now we we find that this is the refrigerant flow ratio which is given as 0.10. This ratio means this is the ratio of the refrigerant flow rate to the flow rate of the gas in the actual refrigerant system. So in this case, it is the ratio of the flow rate of the Freon to the flow rate of the nitrogen. Now here first we see this TS diagram of nitrogen here, and here this diagram will be used to find out the various values of the enthalpy and entropies. So here first we locate the 1 atmosphere line 300 K, and then also the 200 atmosphere isobaric line. So this is the 1 atmosphere isobaric line, this is the 200 atmosphere isobaric line, and here we have the 300 Kelvin isothermal line. Okay, and at these points wherever they are intersecting, we can now find out the value of the H1 and the S1. This S1 is coming from the x-axis, and H1 is coming from the value of these isenthalpic lines are there. So wherever this isenthalpic line is there, you can see from here at top is very near to this axis. So here somewhere here the isenthalpic line will come. So this isenthalpic value you have to take as the H1 value, and here we can do the same exercise for the other H2A S2 for the 200 atmosphere also. So once we do this with this, and second we time we do with this particular isobaric curve. So now then also we find out the value of the HFSF, that is the enthalpies of the saturated liquid. Now here that is from this particular line. Here we find out this isenthalpic this isobaric line. So wherever this is in the two-phase zone, this under dome we have the two-phase zone. So this particular value will be giving us the enthalpy of the saturated vapor, and if we extend it on the other hand, we will get the value of the enthalpy of the saturated liquid. Now this is, now we go to solution. So till before this we just find out the values of the entropies and enthalpies which we shall require to find out the various parameters asked in the problem. So we first go for the liquid yield, and for this we make a energy balance around this particular control volume, which consists of the this liquid reservoir and the heat exchanger and the Joule-Thomson valve, and we find this is the energy balance at steady state, and we rearranging we get this particular expression for the yield of the liquid in terms of the enthalpies. We plug in the values of enthalpies and we find this is the liquid yield, that means about 6.9%. That means the amount of the means out 6.9% of the total gas supplied is converted to liquid. So it is a very, very small value. Okay. And now we go for the work requirement. Again, work, because work is associated with the compressor only, so we take the control volume to the compressor and not any other thing. Even you can, if somebody wants to take the other things also into consideration, that is not going to give a different result. Only thing you will find that you will get some other variables to be considered to find out the work done. So you can, this choice of the control volume is arbitrary. You can choose any control volume, but you have to be careful whenever you are writing all the balance or the conservation laws. So for ease we are choosing only the compressor as the control volume. Now we see that this is the expression for the work, and we again plug in the values. We find the value of the work done by the compressor, and this is the work done by the compressor per unit mass of the gas liquefied. This is for the per unit mass, total mass is compressed. This is the only for the mass of the gas liquefied, and we find these values. So these are the two values we obtain. And now we want to go for the FOM. So for FOM we need to know what is the ideal work, and for the ideal work we find this particular expression. Again, this can be obtained easily from the thermodynamic energy balance, the first law, and we find this is the ideal work, and then we take the ratio of the actual work to the ideal work to the actual work. Why? Because actual work will always be more than the ideal work. So we choose this kind of expression and we get this particular value of the FOM. So it is not a very high FOM we are getting. Now for the pre-cooled Linde-Hampson, this is the particular system we earlier learned, that here this is the Freon system. So this Freon system is pre-cooling this nitrogen system. Okay. So this here we have this A, B, C, D. We found those A, B, C, D and those corresponding enthalpy and entropy values, and now with those we find the expression from the first law of thermodynamics. We make an energy balance under in this particular control volume, and we get this particular expression. And here we see that HC and HD are same because there is a isenthalpic expansion, is HC, this HD, and they are same because they are isenthalpic expansion, and we plug in the values and we find that the this amount of the liquid yield, and what we find that now the liquid yield has increased from a value of about 6% to about 10%. So that is the advantage of having pre-cooling in the Linde-Hampson cycle. Now you see that, let us see that we are getting this 50% increase, and now let us look at the work done. So this is the expression for the work done, and what we find, this is the work done for the unit mass of the gas compressed, and this is the work done per unit mass of the gas liquefied. Again, if we find this FOM, we find the FOM has now increased to about 16%, and this is the increase in the FOM due to this pre-cooling. Now we come to the next part. In the next part, what we find that the pre-cooled liquid hydrogen refrigerator we have, and here we have been given the inlet pressure as 1 atmosphere, the outlet pressure at the compressor to be 100 atmosphere at 300 K, and we are assuming that the compressor is isothermal. Then the mean heat exchanger effectiveness is about this. The nitrogen is compressed from 1 atmosphere to 100 atmosphere at 300 K. The pre-coolant heat exchanger has an effectiveness this much, and the cold heat exchanger in the hydrogen circuit has an effectiveness this much, and both the compressors have overall efficiencies of this 75%, and we have determined the refrigeration effect and the COP and figure of merit for the system. Now here you see this representation that this is the main system, and this main system is being pre-cooled by this particular auxiliary system. So we again, because it is we are going for this TS diagram, and we find the values of these various pressure and enthalpies and entropies, and as earlier. So here we have all these values from here. So it is, I am not skipping it, I am going fast because we know already how to do this, and now we are considering the temperature entropy diagram for the hydrogen. So earlier we did it for nitrogen, now we are going for the hydrogen, and here we are choosing the para hydrogen. As we learnt earlier, why para hydrogen, not ortho hydrogen? Because we learnt earlier that whenever we are storing hydrogen, we do this ortho para conversion earlier, because otherwise what happens, this ortho to para being exothermic, it will release energy and it will re-vaporize the liquid hydrogen. And so we first convert the ortho to para hydrogen and then store it. So that with this logic, what we are doing, we are considering the enthalpy or the thermodynamic diagram for the para hydrogen and not the ortho hydrogen. So we locate all the values of the pressure, temperature, and we get these values of the enthalpies and entropies. Now going for the refrigeration effect. So here we have the refrigeration effect. So this QA is this is the expression, and this is the HS7 prime represents the actual enthalpy due to the ineffectiveness of the heat exchanger. So here we are finding this particular thing. This is the expression we are getting from the by considering the effectiveness, and here we find that this is the value of the heat effect, that is that this much of the energy will be taken up from the refrigerated space by the liquid, and here we find also due to the ineffectiveness this amount of heat is coming down, and you can see very easily if this is 100% effective, that is this epsilon c is 1, then we find that this expression will not be there. So this value, this evaporation effect will be increasing, so this cooling effect is decreasing because of the ineffectiveness of the heat exchanger. Now to find out this for the next problem, this how much heat has been taken off. So we are considering this with a pre-cooled system. If we are doing the pre-cooling system, so we are finding this is the expression for the heat to be absorbed, and again here we are finding this H1 prime and HA prime, these are representing the actual enthalpies, and again this is coming due to the ineffectiveness. So that means we are considering the ineffectiveness of all the 3 heat exchangers, 1, 2, 3. So we are considering all the 3 exchangers, how this thing is affecting the heat to be taken up by this particular refrigerant. So after this we find that again we can see it here easily that if this epsilon and this epsilon p are 1, then we find that this amount of heat that can be absorbed will increase. So because of the ineffectiveness of the heat exchanger, the amount of heat to be absorbed is not is decreasing. So just we are plugging in the values, and we find this is the value of the Z. So this Z is nothing but this mp by m dot, that is the ratio of the precoolant flow rate to the flow rate of the actual process gas. So, this is the value of this Z we are obtaining after plugging in the values of the various enthalpies and the heat exchanger effectiveness. Work requirement is now simple. We are just considering the two systems because total work will be for the actual system as well as for the auxiliary system. So, we have to consider both these systems and taking into account the compressor efficiencies, we are finding this is the amount of work done. And the COP can now be easily found out by doing this particular expression, and we are getting the COP to be very small. So, and the ideal COP is coming to this. So, if we want to find out the FOM, we just take these ratios of these two COPs and we get the FOM to be about 11%. And to know more about this, you can refer to these two books. Thank you.